So by the way, we're talking about CH aliphatic compound, which is actually 296228853, because this is also standard CH bond, has a near 3000 frequency, but since aliphatic compound is at its tail, so its weaker bond observes just below 3000. It's just like finding clues and catching the culprit in the detective game. That's how it works. And by the way, I forgot to tell you like how conjugated bonds work. So there are some extra electrons like double bonds in this part, and these actually rotate because of resonance structure. Because they are same, they just have to be one place away from the other to have some hydrogens around here. So to stay balanced, because this conjugated pi bond benzene ring structure is kind of balanced thanks to Huckel's rule. This is benzene is a this is an aromatic compound. So in Huckel's rule we have 4n plus 2 electrons. So this works here. It works anyway if we have 6 electrons, I guess. But I don't know. But yeah. So the thing is, there is a hydrogen rule too. So yeah. So the bonds here actually rotate. Like this can be bond here. This bond can next time come here. If this bond comes here, it will go here. It will go here, and it's the same exact thing. Like also this one directly come here. It will become first this bond will break, become negative charge here. This bond will break, become negative charge here. This double bond will break and become negative charge here. Lone pair here, and that's how it goes on. So then after that, the bond shifts. It becomes negative charge, then bond shifts, and that's how things work here. So the thing is, that electron rotation actually gives electron supply to these bonds, and obviously, as you know, bonds are formed by electrons, and electrons absorb the light to jump to the excited state. If there is much heavy density of electron, like there can be more possibility of electron in a small space, then obviously it's going to be doing more back and forth, more vibrations, tighter bonds, more energy, more condensed frequency, more light needed to let them jump off. And if more light is absorbed, then there is going to be more gap in the light band which is on the reflector, because it is eaten up by the electron. So obviously you will see much more frequency loss. That's how it works. Okay, I hope you understand what's going on. Now after this, there is C double bond O, and there is Cn. Obviously C double bond O will be the next thing. And why it is, I will tell you next time. So yeah, wait a second. I also have to give you a screenshot, so I would zoom out so you can take screenshot and notes. Yeah, this is kind of visible. Oh yeah, now we're talking, bro, like crazy. So let's go. So I'm gonna erase all this. So our next phrase is C double bond O, which is actually a carbonyl, or we can actually say it is a ketone. And then there will be CN, which is actually cyanide bond, cyanide. And we are going to talk like how it works. So the C double bond O works. C double bond O has the next frequency after this is obviously everything is used up. Only the 1685 and this is left. So 1685 is the greater one. Let's use that. 1685 is the frequency, and left out is 1340 to 1250. And the 1685 is because obviously double bond is stronger. That is stronger. So